Today's lesson is on section 7.3, solve linear systems by adding or subtracting. We're going to learn our third method for solving a linear system in this lesson. We've learned two methods so far. We've learned graphing, which again I think is the best one to start with, because that gives you the nice visual of what's really going on. And when you have two equations, you're trying to find what that point is that those two lines intersect. If you were going to graph them, it's that point where those two lines would cross. That's the point of intersection. That's the solution to a linear system. We also learned substitution, where you don't do that graph, but by substituting one equation in for another one, or into the other one in your system, there's a way to solve around and find one of the solutions, one of the coordinates, like let's say the x coordinate, and then plug that back into one of the equations in the system and find the y coordinate. So both those methods, neither one better than the other. Each one has its pros and cons in terms of some things that can be more helpful, but both great to get you to the solution. We're going to learn the third one here today, which is elimination. And elimination, again, another great way, some pros, some cons to it. Like the method number 2, substitution. If you remember, or if you haven't, if you need more review on substitution, again, I do have a lesson up about that, section 7.2. You can watch that as well. But remember, in substitution, we did sometimes have to have the equation set up so that we can use the method substitution. We need to have an equation solved for a variable. Elimination also, I'm going to talk about, you have to have the equations or the system set up well to be able to eliminate. If it's not set up right or things aren't arranged the correct way, you won't be able to use this method. But once it's set up for elimination, then it is a pretty slick method and can be the fastest, as long as you know how to use it and you can get it set up correctly. So the third method here, as I've gotten right here, what we're going to do is we're going to actually add or subtract these two equations together, and that will eliminate one of the variables. Again, that's why it's called elimination. We're going to look to eliminate one of the variables, either x or y. I have this system right here set up very well for elimination. This is the one's ready to go. We don't have to do anything special or anything different. I can show you the method right now for elimination, what happens. What we're going to do is, like the section title says, I'm going to either add these two equations together, or I'm going to subtract them. And by doing that, that will eliminate one of the variables. So I'm just going to draw a big line, almost like doing longhand addition or subtraction like you have done in the past. And either we're going to add these two equations together, or we're going to subtract them. And by doing that, that should eliminate one of the variables. Often what I'll practice with students in the lesson here in class is I'll have them practice, well, which one do we do in this particular system? Do you think by adding the two equations together I could eliminate a variable? Or by subtracting them? Because that actually does take practice and does take some time for the students to realize which one to do in each particular system. In this system, if we look at these carefully, the first equation, I've got 2x plus 3y equals 11. The second equation is negative 2x plus 5y equals 13. So you have to kind of think ahead and say, well, by doing addition or subtraction, which one will I actually end up having 0 of one of the variables? So when I add them together, almost combine it, kind of like combining like terms, but we're going to do it between the two equations here. When I combine those terms, what will I end up getting? Well, if I look at it here, I think we can see that from the 2x's, I have 2x and then negative 2x. Well, if I add 2 and negative 2, that gives me 0. So that's kind of my key, that if I add these two equations together, that will allow me to eliminate the x's, and we'll see how this works and how I can get to the rest of the solution. But that's what I'm looking to do. First, figure out, do you have to add or subtract the equations together to eliminate one of the variables? If I start adding these together, all you do in elimination then is you add the x terms together, the y terms together, and the constants. And the equal signs, also these need to be lined up too, because that will just come down and be our equal sign in the next part of the problem. So as long as everything's lined up, now I'm just almost going to kind of combine those just like terms. So my equal sign is just going to come down. 2x plus negative 2x is going to give me 0x. And so really I don't even have to write that in. This is why elimination will work. I'll have 0x's, so I don't even need those, because 0 times x would just be 0. So those just kind of drop out of the problem, and that's what we want for elimination to work. 3y plus 5y gives me 8y. 11 plus 13 gives me 24. So I literally just added those two equations together, added all the like terms, like the ones that would combine to give me my new equation. And when I added the x's, they canceled out. That's elimination at its best, because now and using it correctly. Now the x's have canceled out. What do I have left? Is just this one-step equation, 8y equals 24. And I can solve this equation just like a one-step. Divide both sides by 8. Y equals 3. And so now I've got my y coordinate for that point of intersection. Again, if I graph these two lines, they intersect at some point. Well, right now, so far I know the point is something, comma, 3. Going back to the problem, now how do I find out what the x-coordinate is? Well, again, here's where I can kind of plug this number or substitute it back into one of the equations. I'll use the top one in this case, but again, remember, you could actually use the bottom one too. It wouldn't matter because both equations are in the system, so the x-coordinate should be the same in either equation. If I plug 3 back into the top one, oops, now what I'll get is, I'll get 2x plus 3 times 3, which is 9, equals 11. So now I have 2x plus 9 equals 11. So again, kind of like a two-step problem now that I've plugged 3 back in. Subtract 9 from both sides, I get 2x equals 2. Divide both sides by 2, I get x equals 1. So my ordered pair that I'm looking for is actually 1, comma 3. If you did graph these two lines, if you graph them, you would find that they would have two different slopes and they would intersect at some point, and they would intersect at this point, 1, comma 3. So for this method, elimination, to use this, you've noticed that I kind of had a nice one set up here for us to eliminate for a first example. But there are some keys that you need to follow if you're going to use elimination. And here's the ones I'd like you to copy down if you're taking notes along with me. This is the third method we've learned. And for elimination to work, here's what you need to have. So again, like these things I want you to copy down here. These things have to be intact for us to use elimination. Number one, all the variables, the constants, and the equal signs have to be lined up. Equals signs, equal signs, I think I can get that S out of there. All equal signs need to be lined up. Again, I kind of showed you that in this first example, but I had all the terms with X lined up, all the terms with Y lined up, all the equal signs are lined up, all the constants on this side are lined up. As long as those things could be somewhere else in the equation as well, but between the two equations, they have to be on top of each other just like that. So the X terms could both be on the right side, and that would still be okay. We could still use elimination. But they all have to be lined up for this to work. And also, part number 2, a variable in the system. There needs to be a variable in the system that you can eliminate by adding or subtracting the two equations together. And as I'll show an example here soon, sometimes maybe we have to move some things around, or we'll learn some things in the future also that maybe we'll have to manipulate the equation a little bit for us to be able to use elimination. Elimination is a nice, very slick way of solving a linear system. It gets us right to a one-step equation pretty quickly after I've used it. And I can plug that back in and easily find my other coordinate. So it is very slick, but it has to be set up correctly. So as long as we get it set up, then I can use this method. So all these things in red you've already written down if you're taking notes along with me. I'm just going to keep them on this page as well so I can reference them. But again, there's our 3 methods, and the third method, there's the things we need so that we can use elimination. What I want to talk about is this next example. I'm going to go through a few examples here with you. This one says 4x plus 3y equals 2. And 5x plus 3y equals negative 2. So this system, again, what do we need to be able to use elimination? Let's say we're deciding I want to use method 3 so far. I want to use elimination. So to use elimination, what do we need? Well, we need all the variables, all the constants, all the equal signs lined up. So do I have that? Yes, I do. Here's the constants on this side, 2 and negative 2. Here's the equal signs. Here's 3y and 3y, and here's 5x and 4x. So yep, I've got all those things lined up. I can use elimination. At least I've checked number 1. Okay, number 1, yes, criteria, I can use it. Number 2, a variable in the system that you can eliminate. You need a variable in the system that you can eliminate. So now I need to either determine, can I add or subtract these equations together and get rid of one of the variables. If I look here, I have 3y and 3y. So this tells me, yeah, since I got the same number there, that's probably a good hint that I can eliminate those. In this case, I'm going to subtract. Now, here's what I'm going to suggest for when you're going to subtract two systems and use elimination. I often have students who try to use subtraction, and if you don't do it kind of the way I'm going to show you, I see them run into a lot of small mistakes or make errors very often, like little errors, but errors that throw them off, and then they don't get the right answer. So here's what I'm going to suggest that you do when you're subtracting, use elimination. Instead of subtracting, just kind of like how you could say, well, I have 7 minus 10, some basic problem like this. In the past, we've worked on, well, if I'm taking, let's say, negative 7, just to make it a little more like problems we've done too. Negative 7 minus 10, well, what I tell students sometimes is you can change this into plus negative 10. I call it chop dash because I chop that subtraction sign. I have minus 10, but what I do is I chop the subtraction sign, and then I dash right here to make it negative 10. So again, that's why I call it chop dash. Is when I refer to it in class. Chop dash. Because I'm chopping it to make a dash addition and then dashing to make it subtraction. So I'm sure, student, if you're following along with me, you've probably heard me say that before in class. What I recommend is that you chop dash this problem as well to make it work. But you just have to dash everything or change the sign. I could say change the sign of every term in that second one. So you could try to say, okay, 4x minus 5x. 3y minus 3y, 2 minus negative 2. But what I find is if students don't do the chop dash, and they just try to do it in their head like that, then sometimes they forget by the third term and the second, maybe sometimes even just the second term, that they're supposed to be subtracting. And then they'll add instead or do something they're not supposed to be doing. So here's my recommendation. I would chop this addition sign, so I'm going to make this plus, and then I'm going to dash or change all the signs of everything here. So this 5x is going to become negative 5x. This 3y is going to become negative 3y. And now I'm going to make this positive 2. If I do that, and now I just add, now I don't have to always be looking back and saying, okay, I'm supposed to be subtracting here. And it seems like adding is just a little easier in our brain usually than subtracting. So I think this is a little bit easier method or a little bit easier way to take care of that if you're going to subtract the two equations. Just make it addition. Make it addition, but change all the signs of the one you're going to subtract. Now I can say 4x plus negative 5x gives me negative 1x. 3y plus negative 3y gives me 0y. So again, I would have like plus 0y there, but I don't even have to write that in because 0 times y would be 0. So those would just disappear. And then over here, I'd have 2 plus 2, which gives me 4. So my new equation is negative 1x equals 4. Divide both sides by negative 1. I get x equals negative 4. So there's my x coordinate. And if I want to plug negative 4 back in and find out what my y coordinate is, I can do that. Let's plug it into this top one. It really doesn't matter which one I plug it in, but let's plug it into the top one. So now I'm going to get negative 4 times 4 is negative 16 plus 3y equals 2. I'm going to end up adding 16 to both sides. I'm going to get 3y equals 18. So it looks like y is going to be 6. I'm going to get negative 4, 6 for my point. If I graph those two lines, that's where the two lines would intersect at that point, negative 4, 6. Going through another example here. In this one, as I look at this system, it says solve the system. We're going to try to use elimination. If I look at criteria 1, it says all the variables, constants, and equal signs need to be lined up. Well, looking at this one here, I see the equal signs are lined up, right? But then these aren't both y terms, so that doesn't work. And this is x and y, and this is 8x and 14. So no, I can't eliminate yet. Okay, I can't use elimination right now. I just have to move some things around, and then I could use elimination, but it's not at this point. If I look at these equations carefully, what I do notice is that in the second one I have x and the constant on the same side and y is on the other. So I think I can modify this top equation. If I just subtract 8x from both sides, something we've done in the past, if I subtract 8x from both sides, that will get my x term on the right side. Now this one has turned into negative 4y equals negative 8x minus 4. And now I haven't lined it up quite yet, but I can see that I've got the x term, the constant on one side, here's the equal sign, and then the y term. And that's what I've got really on this one. I just got to flip it around. So I'm going to take this equation now, and I'm just going to kind of turn it around as well, so I can get the x term on the other side. So now if I turn it around, I could write it like this: negative 4 minus 8x equals negative 4y. And so that's just that same equation, just kind of flipped around, as I said there. but it is actually the exact same equation. I just kind of changed the order a little bit to help myself out. Now that I've got it set up, I've got the constants lined up, the x terms lined up, the y terms lined up, the equal signs lined up. Now I can use elimination. So now it's set up correctly. So again, that's just one of the big first steps, though, is we do have to realize when a problem is set up for elimination and when it's not. In this case, it wasn't, so I got to move some things around. Now I can use this method. In this one, I think if I add the two, linear equations together, I think it should be able to solve it for me. So 14 plus negative 4 gives me 10. 3x plus negative 8x, just kind of remember too, the sign in front of the 8x says subtraction, so I have to think of that. I could chop dash it too, but I have to just think of it like negative 3x or 8x. So 3x plus negative 8x is what's happening there. That would be negative 5x. And then 4y minus 4y or plus negative 4y is going to cancel those out. So that'll be 0y, or I'll just have 0 over there, which is fine. That can happen. Now I've got this equation, 10 minus 5x equals 0. Well, it looks a little funny, but if I can just get the variable by itself on one side here, like add 5x to both sides, then I'll have 10 equals 5x. And now I can divide both sides by 5 and get x equals 2. So yep, because I was able to cancel out the y's using elimination, I still got something I could solve. I got x equals 2. And now I can plug 2 back into one of the equations. And again, it doesn't really matter which one of the originals I use. It should give me the same answer. I'll go back to this one right here. Plug 2 into this spot. I'm going to get 14 plus 3 times 2 gives me 6 equals 4y. So if I add those together, I get 20 equals 4y, and divide both sides by 4, I'm getting y equals 5. So now I've got my solution in my system. The point where these would cross would be 2. Those two lines would cross if I graph them at 2, 5. Again, elimination. Just kind of summing it up here. Good method. But I do have to check my criteria here first to make sure that everything's lined up so I can use elimination. And like I said, also, if you're going to decide to subtract, just make sure you chop dash all the terms in that second equation. That does make it a little easier to do the subtraction for eliminating.